United football, both domestically and abroad. We start with the absolute premiership. Mamelodi Sundowns away to Brooklyn Men Celtic tonight. Orlando Pirates host Golden Arrows. Black Leopards play Barrow Neville. Chippa host Free State Stars. Last night, Fritz went top of the table with a 2-0 win over Cape Town City. Kaiser Chiefs are second after a goalless draw with Highlands Park. Amazulu, Maritzburg also goalless, while Queen City and Supersport play out to a 1-1 draw. Champions League action continues tonight with Borussia Dortmund up against Monaco. Spurs have a very big task on their hands. They host Barcelona tonight. Napoli play Liverpool. Will be a good game as well. Napoli looking very good in Serie A. PSV will play Inter Milan. Last night there were wins for Juventus and Benfica, while Man United, I told you yesterday, and Bayern drew. Real Madrid lost.
Yeah, that's good watching the Man United. That's so boring.
Well, I'm surprised you weren't one of the ones that stayed awake and booed the men off the park. For those that were awake, it was terrible. The final whistle went, and the owner fans that were there on the field were booing them off the park.
I can understand.
That's how bad.
Boring, man.
That's how bad it was.
You know what? I wanted just to mention this. You say Barca playing again tonight.
Yes, Spurs.
I saw the story, and it's a remarkable story of what football is all about. Now it's about money. FC Barcelona yesterday announced that it has become the first sports club to post annual revenues exceeding $1 billion. La Liga champions Barcelona presented their annual accounts on Tuesday, showing earnings of $1.05 billion for the 2017-2018 fiscal year, breaking its own income record for the fifth successive year, posting a profit for the eighth consecutive year.
$1 billion. Wow. Lionel Messi effect.
You know how they got most of the money? From selling Neymar.
Really? Yeah, jeez. It's only 200 million, so it's got a long way to go.
Yeah. They sold, August 27th, sale of Brazilian forward Neymar to Paris Saint-Germain for a record 222 million euros, which is $257 million.
Yeah, it's not bad. Like one sale, like $250 million. Also, Neymar worth the money? Yes or no? That's another question. Frontiers up against Zimbabwe in the second ODI today in Bloemfontein. It starts at 1 p.m. Victory for South Africa will wrap up the series with a match to spare. And finally, Kevin Anderson is through to the second round of the China Open in Beijing. Coming from a set down to beat Australian Matthew Edmonds 4-6, 7-6, and 6-2. Mark Lewis, EWN Sport. EWN Traffic.
Good afternoon. In the traffic at Liverpool Park, there's been an accident on the M3 South, the start of the Harbour Drive exit. Traffic is stopped at M1 South as you're approaching.
I once met an astronaut. Not an astrophysicist.
Neville, we're broadcasting.
Oh, well, that's useful information.
Ladies and gentlemen, please take your seats and test your sound. We're going to be starting in just a couple of minutes. Thank you. Okay, need to look that way. Good afternoon, ladies and gentlemen. Thank you very much for tuning in to this, the first online broadcast of the 2018 Habitable Planet online workshop. It's a pleasure to have you all here joining in from all over the country, and it's my great pleasure to introduce to you our panel today, who are going to go through your questions. Firstly, for the panel, just to say that we've been doing a 10-week online course entitled The Habitable Planet. And as part of that course, we're looking at all the various reasons why planet Earth is habitable. And so far what we've done is we've looked at astronomy, we've looked at a bit of physics, and just now this week started to touch on paleontology. And we've got a whole bunch of students out there who have sent questions in. I have your questions in my hand, and we're going to have an attempt to help you with any things that you've missed from the work, or maybe just have some discussions that go a little bit beyond what we've done in the course. I know that there's some big groups out there I've heard that we have PMB, hello PMB, Unizulu, Univenda. I heard that Walter Zulu are having some trouble connecting. I hope you get there soon, but close by, the University of Fort Hare, hello to you guys too. I'm going to get our panel today to introduce themselves before we kick off. And what I'd like to do is ask them to just each tell the audience a little bit about what they do, and also to answer one of the students' questions. Before I mention that, I should point out that I need to apologize for one thing, which is that you may well be able to hear I'm originally British, and so I struggle a little bit with some of the names from South Africa, both Afrikaans and African names. So if I murder your name, I really do apologize. I will do my absolute best to do justice to everybody's name. So what I'm going to do is I'm going to ask the panel to have a quick introduction to themselves, and maybe I guess I should do me as well, and then answer one of the students' questions. And that comes from Nontokozo Mpala, who asks, what's the most interesting thing about being an Earth system scientist? So I will start to my right, and I'd just like to ask each of the panel for a quick introduction, please.
Okay, hi everyone. I am Belinda Monyela, a first-year PhD student at the University of Cape Town, and I study the Southern African climate. So my PhD focuses on the impact of El Nino on Southern African climate. And from our question, what is the most interesting thing about studying Earth science systems? It's because it's complex. So that's where the fun is. You get to understand that the systems don't happen in isolation, so they interlink to each other, and then the moment you think you understand the system, the moment you know that like there's more to know. So like the whole complexity of it makes it fun. Yeah, thank you.
There's a famous quote about quantum mechanics, right? That anybody who says that they understand it clearly doesn't.
Yeah.
Okay, hi everyone. My name is Asmita. I'm currently also a first-year PhD student of Oceanography, but registered at Stellenbosch University. And I'm also part of the CSIR, the group called SOCCO, Southern Ocean Carbon Climate Observatory. And my PhD is centered around looking at the iron and light levels in the Southern Ocean. Originally, I did my undergrad studies until master's in physics, and now I've done a field change into oceanography. And the question about why am I studying Earth system science? Invariably, this is where we live. We need to know about our area. It's our home. So knowing about the planet is basically knowing about our own home, where we live, how to take care of it, and yeah, enjoy living here. Thank you.
Good afternoon, everybody. My name is Tshiamo Moleele. I am currently doing my honors in applied geology at the University of the Western Cape. My project is mainly focusing on the geochemistry and the geochronology of the minor plutons of the Cape Granite Suite. And to answer the question of what's so interesting for me about earth scientists is that we get to understand the past, and for you to understand the past, it makes it easier for us to plan for the future and to not make the same mistakes as the past.
Thank you.
Hi everyone, I'm Imogen Whittam. I did my PhD in astrophysics at the University of Cambridge, and now I'm a postdoctoral fellow at the University of the Western Cape in the physics and astronomy group there. I research galaxy evolution, so how galaxies like our own Milky Way formed and evolved. I'm particularly interested in what we call active galaxies. So these are galaxies where a lot of gas and dust is falling into the central black hole, causing a huge amount of energy to be released. So these are extremely powerful, bright objects, and I find them really interesting. In terms of the question, what's the most interesting thing about what I do? I essentially get to look back in time because I'm looking at really, really distant objects. So the galaxies I'm studying at the moment, the light I'm seeing actually left those objects before our Earth had even formed. So I think that that's the most interesting thing about what I do.
Okay, thank you. And then lastly, we have joining us remotely, all the way from the grand city of Muizenberg, we have Neville, if you'd like to say. I think your microphone is on, go ahead.
Can you hear me?
Yes.
Good. So hi everybody, my name is Neville Swiejd. My job is that of the director of the Access program, and the Habitable Planet program is one of our activities, or one of our sub-programs. And to answer your question, I thought about saying that I didn't really know that I was an Earth system scientist until fairly recently, actually. I started out as a marine biologist, and I worked, my PhD was at UCT, and I did it on the molecular genetic applications in fisheries, specifically working on what's known as a perlemoen or an abalone. It's a local species of mollusk. And then I moved along in my career, and now I work on public health, which is very different from where I started. And I also run the program. And I guess that illustrates the point that there are various different disciplines within our world of natural science that come together in this space called Earth system science. And so really what I enjoy about it is that it's so multidimensional and so interdisciplinary, and really does bring together various strands where every specialization has a role to play in understanding Earth systems. So that's really what I enjoy about being an Earth system scientist.
Nice one. Thank you very much, Dr. Neville. I suppose I should very briefly say a couple of words about me. Bearing in mind, I think most people actually know me already, but just for formality, my name is Carl Palmer. I work for Access alongside Neville, and I am the Access Education and Training Manager, but I actually was a scientist at some point in the distant past. And when I was a scientist, I did a PhD in atmospheric chemistry, and I studied the interactions of chemicals that seaweed produce in the air just above the oceans. So I had a little bit of a link to the people in oceanography. I used to go out on ships, but also a little bit of a link more to the atmospheric physics side of things. Okay, so that's everybody introduced. We have an excellent team here today. We're about to dig into all of your questions. What I want to say is that you guys had a huge amount of questions, and we can't possibly answer them all in one session. What I am going to do is I'm going to get the Access elves to type up some of the answers to the questions later on. And we've also got one scientist who was supposed to join today who can't actually be here, and he's going to put together some of the answers to a few of the astronomy questions, and we're going to put that as a video on next week's course. So I want to apologize. There are really so many good questions you guys asked, and we can't do justice to them all. What we have done is we've tried to pick a few of the interesting ones that we'll just have a bit of a discussion around, and also will hopefully help with some of the questions from this week's test. So do stay tuned for that. Okay, so what we're going to do to go through the questions is we're going to try and do it in the order of the course. I've grouped it roughly according to week, and I'm just going to have a little bit at the beginning of each week's work to have a quick discussion of how that work fits in. The first week we did my lecture on In the Beginning, and then we had Tshiamo talking about Not Too Hot. So I'm going to start with just a little bit, and everybody, when I ask for these, 1-2 minutes, just looking at how your discipline or how that area really contributes to a habitable planet. When we looked at Not Too Hot, when we looked at In the Beginning, I took you guys back through your family lineage, looking at the journey that you'd all taken to starting this course. It seems a long, long time ago now. It was only 4 weeks ago. And we then went back even further than the first species on Earth and decided to think about why is it that we actually have an Earth rather than nothing at all? And why is it that that Earth that we do have is made of the right sort of thing? And I think if you remember that to answer those questions, we had to call upon something called the Big Bang Theory. I made some observations that the universe is expanding, that how we can measure that using the Doppler effect and redshift. And we looked at the cosmic microwave background radiation and how it all pointed to the fact that all of the matter in the universe was at some point in one place, a place we call a singularity, and that it expanded from that singularity around 14 billion years ago. And I here highlighted some key things that at the start it was very, very compressed and very, very hot. That meant that atoms didn't form. Atoms only formed about 300,000 years into the life of the universe. And of course, we need those for a habitable planet. But that what actually formed from the Big Bang was then only helium and hydrogen. And we learned that we're made of carbon, oxygen, phosphorus, and nitrogen. And that all of those things, we had to wait till even longer into the life of the universe for those to be formed in stars. So without going too much that we're going to answer the questions, is there anything, Imogen, you want to add from an astronomer's point of view? Why is learning about the Big Bang important to understand why Earth is habitable?
So I think the key thing to remember about the Big Bang is that actually all of space and time was created in the Big Bang. So everything was created at that point, so that you can't really think about the concept of before that. But yeah, everything else you said, I think that pretty much covered it. Yeah,
we'll come on to that. And that's a really mind-blowing and difficult to grasp concept of the Big Bang.
It's very hard to get your head around.
The time was created, but yeah, we'll
interesting concepts to think about.
Can I ask you a question of Imogen? Am I allowed to?
Yeah, absolutely.
Imogen, the idea of the Big Bang, is that a theory, or is it something which is really generally accepted in the scientific community? Does it still remain as a theoretical concept, or is it something which is generally accepted as correct and true?
So it's both of those things. It's a theory, but it is very much generally accepted amongst the scientific community. We have very strong evidence that the Big Bang did happen and that the whole universe was created from a singularity in the Big Bang. So it is a theory, but there's very strong evidence for it, and it is very much accepted in the scientific community.
I think that's worth adding on to, Neville, that just in scientific parlance, what's the word? In science, just because something's a theory doesn't mean that it's not very well supported by the data and widely accepted. I can only think, because of the nature of science, which we might come on to a bit, I can only think of one or two cases where we call something a law, which is the point where we think it's not going to change. But even that's not ironclad. We had Newton's laws of motion, but then they were replaced to some extent by Einstein. So I think it's important to also just emphasize that just because something is called a theory doesn't mean that it's not widely accepted or widely supported by the data. In fact, science really is, the body of science is facts and theories, right? Laws, I don't know, do we have, how many laws do we have?
And I think that laws is more of a kind of old school thing. These days we have, that's how science works. We have theories and we test them and they become generally accepted, but they're still called theories.
Sure.
Because we can always refine our theory.
And it will come again in a little bit later. It's a big difference between science and almost any other system of thought, that there is no final answer.
Yes, we're always refining our answer and making it slightly better. That doesn't mean that the previous answer was wrong. It just means that we've improved it slightly.
Yes, absolutely, absolutely, perfect. All right, I think at that point then let's just dive into it because we're starting to get to some of the questions. I am going to start with Prince Madziba's question. Prince says, looking back at Dr. Palmer's lecture, the concept of a singularity in the Big Bang makes logical sense when looking at the Doppler effect, the redshift and afterglow. The question is since this is a singular point houses the entire universe, did it not have mass already and hence a gravitational pull? And I guess the inference is then, why would it expand?
Yeah, so the key thing here is what I mentioned earlier, that all of space and time was created in the Big Bang. And so gravity is a force experienced by objects with mass. It's what's keeping me on my chair right now. But for gravity to have an effect, you need space, because gravity actually works by bending space. That's what Einstein showed, and that's how gravity works. So without space, you can't have gravity. And because in the Big Bang, the whole of space was created, you can't have a gravitational force, any kind of gravitational pull, without space. So you're right in saying that that singularity housed all of the mass, but it also housed all of the space. So that can't have a gravitational pull on anything else. It's a slightly odd concept to try and get your head around, but I hope that answers the question a bit.
Yeah, it's nice. It links in a little bit to the next where we're going, but maybe just pull back one step. But then once everything has been created, what's the force that's pushing it out? Because you would expect with all of that mass, it would have a huge amount of gravity pulling it in. You would expect a black hole, basically, right?
Yeah, and I mean, this is quite an interesting question, and it goes on to sort of links to what's going to happen next. Is the universe going to keep on expanding forever, or is there then some force that's going to make it come back in, or is the gravity going to make it come back in and collapse into a kind of big crunch scenario? But basically, there's a force called dark energy that is causing the whole universe, that's causing that expansion.
Okay. So that's dark matter and dark energy are two really big things in cosmology, right? They're called dark because nobody's found them.
Yes, and because we can't see them. So dark matter doesn't give off or interact with light. So that's why we call it dark. Yes.
Okay. So then the next question I want to go to, which does link onto that, is from Ntombopolo Mamayo, who asks, so if we accept the Big Bang Theory, please explain the conditions that prompted it. And I know you've answered that a little bit, but it is a question. It comes up every year, and every time I present this, what caused it?
Yeah, it's a really interesting question, and again, it's one of these things that's kind of hard to get your head around. But there's no such thing as before the Big Bang, because time itself was created in the Big Bang. So you can't. There's no concept of before the Big Bang, so we can't talk about what caused it. And one analogy that's often used is it's like saying what's north of the North Pole. Like, there's nothing north of the North Pole. That is the most north point. You can't go north of it. And in the same way, you can't go further back than the Big Bang. So basically, there was nothing before the Big Bang. Time didn't exist. So then it's very hard to think about what caused it. We can kind of philosophize about various scenarios. One possible scenario is there was a previous universe. That previous universe collapsed into a big crunch, and then you had another Big Bang. But that's very much the realms of sort of philosophy. That's not a theory that we can ever test. So, but they're interesting questions to ask.
Yeah, I like the analogy of the North Pole. I think I remember seeing that somewhere before. So you could almost imagine that the singularity is the North Pole, and the universe expands off in every direction as the Earth expands off every direction, and asking what's north of the North Pole becomes a redundant question. And I really like that explanation, actually, until I thought about it, and then I remember being at primary school and asking where God came from, and a teacher telling me, well, it's just like a circle, there's no start or beginning, and me thinking, that's nonsense. And so it's the same logic being applied. Anyway, I digress, but it is one that comes up, and it is one that becomes difficult to get your head around.
Absolutely.
And so linking in a little bit to what Neville just asked, Lafuno Razila asks, can the Big Bang Theory ever be replaced?
Yeah, this does link into what Neville was saying. So the Big Bang Theory, we have a lot of scientific evidence for things like the way that we see all of the galaxies moving away from us, and the further galaxies are moving away faster, suggesting that the whole universe is expanding, and therefore, if you reverse that, it previously all came from one point. We've also got things like the cosmic microwave background, which I don't know if you've covered, and Big Bang nucleosynthesis, the proportions of the different elements that we see in the universe, they exactly match the predictions that are made by the Big Bang Theory. So there's very strong evidence for the Big Bang, and in fact, all of the evidence that we've looked for, everything supports the Big Bang Theory. But it is a theory, and I think it's extremely unlikely it would ever be entirely replaced, but it could be refined. And particularly our understanding of what happened in the first few seconds after the Big Bang. Some of that is still not certain, and that those models very much could be refined on the basis of more evidence. So this kind of goes back to our discussions about how the scientific method works. We have a theory, we collect evidence, and we use that to confirm the theory or to help us to refine the theory. So I hope that answers that question.
Yeah, I mean, it makes perfect sense. Yeah, I thought you were coming in. Yeah, it's a really interesting one, that science never has this right answer. We just compile the available evidence, and whichever theory fits the available evidence best is the one we go with. The idea that it never comes to a right answer makes it sound like an absolutely useless field of work, because who would ever want something that never comes to a final answer? But the analogy I always use is with electrons, that particle physicists have still no idea what an electron is. Nobody's ever been inside an electron. Nobody has really any good idea, and yet your phone works. And the fascinating thing about science is that it delivers progress, right? Even though there's no right answer at the end of the day, my cell phone works. So I don't really question the physicists when they tell me about electrons, even though they don't know what an electron is, because it delivers such incredible progress. And again, with the Big Bang, I guess we've got to the point where there are around 100 good bits of evidence all pointing to the same thing. So you'd need suddenly, just one new bit of evidence wouldn't overturn the theory just yet. You would need another 100 pointing to something else, which seems very, very unlikely, as you've said. What's more likely is if another bit of evidence comes up that does contradict one aspect of it, that we then have to refine the theory. And so it's science's great weakness and great strength. The weakness is you never have a final answer, but the great strength is that the answer is always getting better with more evidence. But yeah, once again, I could go on forever, so let me...
Well, I think the other thing to point out about you saying we never have a final answer, part of that is because every time we answer one question, we come up with 10 more questions. And then for each of those 10 questions that we answer, there are 10 more questions. So we're making huge progress, but, and this goes back to what you were saying about things being extremely complicated. The more we understand, the more complex we realize things are, and so the more questions we have.
Okay, perfect. One question, and this is something that I did fail to cover in my lecture, so I definitely want to get it in, is Kamolego Moshidi asks that they would like to understand how stars are formed.
Yeah, this is a really interesting question. So essentially, in the universe, there are large clouds of gas and dust. And these clouds have some turbulence, and so you end up with slightly denser clumps of gas and dust. And those denser clumps then collapse under their own gravity. So they get denser and denser, and they have to cool a bit to do that. And so as they get denser and denser, they start heating up in the center. And so you get this clump of gas that's getting denser and hotter until eventually the center gets hot enough that the hydrogen has enough energy that it will fuse to form helium. And that's nuclear fusion. That's a hugely energetic process. And so that's when the star starts glowing. And that then produces enough energy in the form of radiation pressure that then stops it from collapsing any further. So you end up with a star, which is a ball of gas that's glowing extremely brightly and is being powered by fusion. And that stops it collapsing any further. For a star like our sun, I think it takes about 50 million years to go from a sort of cloud of gas and dust to a star like our sun.
Okay, I want to pick up on our sun in a minute.
Okay.
But I've got a question from the WhatsApp group. Okay. From Andy. I don't have any more of a name than that, I'm afraid. But Andy asks, because I think it's linked to this, is about black holes. Mm-hmm. He says, I've only seen black holes in the movie. I want to know if they really exist, and if so, what are they made up on? And has anybody actually ever been into a black hole?
Yes, so to answer the first part of that question, black holes definitely exist. We have very strong evidence that the black holes exist. There are two main types of black hole. There are what we call supermassive black holes, and they're in the center of every galaxy, including our Milky Way. So every galaxy has a really, really massive, so about 10 million times the mass of our sun, black hole in its center. And we know that's the case for almost every galaxy. There are also much smaller black holes, which we call stellar mass black holes. And these are created at the end of the life of giant stars. So I was talking about how stars form and how you end up with something like our sun. If you've got a star that's a bit larger than our sun, it'll continue burning all of its fuel in this fusion process, like I was talking about. And then when it reaches the end of its life, it'll collapse further. And eventually it'll explode in a giant explosion known as a supernova. And for massive stars, what you're left with at the end is a black hole. So they're the kind of two main types of black holes, the supermassive ones in the center of galaxies and the ones that are caused by the end of a star's life cycle. I think there were more parts to the question, but I've got slightly sidetracked.
No one has.
Okay, so no one has been inside a black hole. One of the key things about a black hole actually is that there's a point called the event horizon, and once you get inside that point, you can never get out. Nothing can come out. So not even light can escape from a black hole, which is why they're called black holes, because they appear black.
Like a never-ending.
So even if someone ever did go in a black hole, they'd never be able to get out, and no information can get out. So they'd never be able to tell us that they were inside and what it was like inside. So
I have a question. So I'm a strict scientist, so I don't know anything about the black hole. So where do we find them? At the surface, or the stratosphere, or where do we find them there?
Where do we find black holes? So in space, so in the center of galaxies, and also just kind of within a galaxy, there'll be lots of these smaller black holes. So just kind of sitting there in space.
I guess you could say they're kind of like just freely there.
Yes. In the same way that you might have a star. Instead of a star, you'll have a black hole.
Oh, okay.
So they're just in space, normally inside a galaxy.
I have a question. Do they ever collide, like how stars and
Yeah,
planets keep colliding?
so that's a very interesting question. And very recently, we've discovered that they definitely do. Because I don't know if you've heard of gravitational waves and LIGO. And there was these big announcements and big discoveries that were made within the last couple of years. And so what they've actually detected is pairs of black holes. So you have a pair of black holes that will be orbiting each other, and they'll eventually spiral together and collapse. And they've detected the signals from those black holes colliding. And that was actually something that Einstein predicted would happen. He predicted that you would have these black holes, they would collide, and they'd produce these gravitational waves. And that's something that has been detected very recently. And in fact, that's an example of a theory where the theory of, in fact, general relativity predicts that you'll get these gravitational waves. And so they built an instrument, LIGO, to try and look for them, and then they found them. And so that provides further strong evidence for general relativity and for black holes and all of these theories that we have. So.
Very quickly, it's taking a step back on WhatsApp. Prince asks about multiverse theory, and does that contradict the Big Bang?
Yes, so the short answer is no, it doesn't contradict the Big Bang. We can't get any information for anything outside our own universe. So it's perfectly possible that there are multiverses out there, but this is very much in the realms of philosophy, not science, because it's not a theory we can test.
Okay.
So possible, but who knows?
Okay.
And it doesn't contradict the Big Bang theory.
There's almost, it's possible, right, that it complements the Big Bang theory, that possibly there are multiple universes with different parameters. And that explains why this one has nice ones for us.
Yep, absolutely.
Also possible. But okay, I don't want to drift too much down the sort of theoretical cosmology line. I'm going to bring it a little bit back towards the course. I want to make a note that the next series of questions sort of overlap with something that's coming up later in the course, that we are going to start thinking about life a bit more. So far, we've only just really introduced a physical model of the Earth. And both of these interact a little bit. So we have a lecture coming up next week on the origins of life, and also next week on amazing water, about why water turns out to be so incredibly special and important to life. But nonetheless, while we have Imogen here, I'm going to just get her to have a go on that. And this comes from a couple of questions. They're linked from Poncho, Mashir Lahako, and Paluda Tivane, who ask, firstly, is life possible on other planets? And then linked to that, scientists have discovered water on Mars. Does that mean it was once habitable, or does that make it habitable, or was it once habitable?
Okay, so starting with the first part of that question is life possible on other planets? Essentially, we don't know yet. What we do know is that there are a lot of other planets out there. The Kepler telescope has recently discovered a lot of planets around other stars that aren't our sun. And we now think that at least half of the stars in our galaxy have got planets around them. And there are hundreds of millions of stars in our galaxy alone. And half of them have got planets around them. So that means there are a lot of planets out there. And so some of those planets must have the same conditions that we've got on Earth. They must be at about the same temperature, have the same kind of elements. So there are almost certainly other planets out there that have the same conditions that we've got on Earth. So therefore, conditions are possible for there to be life. What we don't know is, does that mean there is life? Yeah, I don't know.
it would be probably the greatest scientific and philosophical leap ever if we discovered life on another planet, right? That would completely change the way we think about being human at the end of the day, and also it would have to completely change my course, because I start the whole course by noting that out of, I think we know about 10,000 exoplanets
now. Yeah, something like that, and the number's growing every day.
But that so far we only know one to be habitable, and then we consider what's special about it. I would have to completely rewrite that line. So on some level I'm hoping for it, and on some level it's a lot of work for me. Okay, I'm going to move then from the first talk. Let me just see, is there anything here? Could you just catch up if there's anything that we want to do online? But as she does that, I'm going to start to move on from in the beginning to the second talk, which we had, which was not too hot, not too cold, looking at how the Earth's position relative to the sun helps us, or doesn't, in fact, help us explain its habitability. Tshiamo, can you give us very, very short, what did we take from that?
Essentially, what we took from that is that the Earth is in fact too cold for us to live there.
Or would be.
Yeah, would be, like hypothetically. So yeah, that's what we took from it.
That was very short. Thank you very much.
Yes, for short.
About the sky.
We have a question from online. Oh, okay,
Yeah,
the sky,
it's
we'll deal with it. It's coming up later, and very soon, in fact. And I've got one there, but I'll come back to that now.
Maybe quick question. So
Sure.
one of the students would like to know about any factual movies that they can watch about space or even Earth systems in general.
Okay, space. Well,
So do you mean in terms of movies,
Factual,
like
a documentary?
a documentary rather than
It's
kind of?
Planet documentary, the BBC documentary. So
Is it a series?
yeah, the series.
Yeah, no, there are some great BBC documentaries. I don't know which ones are available.
There's one
Yeah.
called, I think it's Blue Planet.
Blue Planet, yeah.
Blue Planet. That's very informative.
And certainly Brian Cox has done some TV series about space that are very good. In terms of popular movies, which I thought was the question initially.
I think he meant movies.
Yeah, but I was just going to note that Interstellar is actually very scientifically accurate in terms of the way it displays space-time and those kinds of
Carl
things.
Sagan.
Yeah.
So any movies that are based on the works of Carl Sagan?
Interstellar, remind me.
So it's the one where they go to different planets. Google it.
Okay.
I'm not a film
fine.
critic.
Also, there were a few.
That movie about Mars is very good. What was that recent one with Brad?
The Martian.
The Martian.
Ah, yes.
Very good movie. But there's always, from my era, there's Carl Sagan's Cosmos, which I'm quite sure is out of date now, but there's a lot in it, I think, that is still very valuable to see.
Yeah, I think, as you said, Brian Cox is very good. I think
yeah.
it came from both of you. Sort of younger and more British Carl Sagan. Carl Sagan
good
for this video.
description.
So for moving back to the Earth's position, so in Tshiamo's lecture, she set up this simple model where what we did is we really kicked off our course by trying to simplify the problem of why Earth is habitable, getting rid of all of the complexity from the Earth. So we got rid of humans and animals and birds and oceans and the atmosphere and stripped away everything to make a model Earth, which is just a ball of rock of a given color. We learned about the idea of albedo, at our distance from the sun. And Tshiamo presented a short calculation of something called the effective temperature. So the effective temperature, and this comes up in the exam questions, the effective temperature is really what the temperature of the Earth should be if the Earth was just this ball of rock. It's a model for the Earth. And Tshiamo's model is really useful, and we're going to come to modeling a little bit later. But Tshiamo's model is really, firstly, it's wrong, right? It's not real. We know that Tshiamo comes to a value of -18 as the average temperature from the Earth. Even people who are not from Limpopo will realize that -18 is far too cold. So it's not right, but it's really useful because we understand the assumptions that go into it. We understand what's missing from it. And so then we can infer something. And Tshiamo compared the effective temperature of Earth, Venus, and Mars, and found that all of those three should be far too cold if they were just these simple balls of rock with a given albedo at a given distance from the sun. So the big conclusion from that is that it can't just be that the Earth happens to be the right distance from the sun, which is always fascinating in the search for exoplanets. They're always absolutely, they're fascinated with trying to find ones the same distance as Earth, but actually it's not just the distance. The Earth is quite unique in ways which we'll come to, which allows it to be habitable at that distance. It should probably be a lot closer if you wanted it to be habitable without its various unique features. But we'll come to that. I'm going to go into the questions. Are you happy we're covered?
Yeah.
Okay. Just the one question really on that, which comes from Brilliant Dubé, who asks, why is the effective temperature of Venus lower than that of Earth, given it's closer to the sun? Which is a great question, and also one which I believe is either on this exam or on the last one, so definitely worth bringing up. And so I'll give a very brief answer to that. So obviously, as I just said, the effective temperature is this model where we've taken everything away, right? So the fact that Venus's effective temperature is too cold cannot be to do with its atmosphere. It can't be to do with anything other than the distance from the sun and its color, right? And as you've said in your question, the distance from the sun is also not the right answer because it's closer. It should be warmer than the Earth. So we're left with, by a process of elimination, color. And that turns out to be the right answer. Venus, the surface of Venus is a very, very light color. It therefore has a high albedo. So even though it's closer to the sun and therefore receives more incoming solar radiation than the Earth, it rejects most of it. And so actually, fascinatingly, it's such a light color that Venus should be freezing cold. Actually, Venus isn't. It's incredibly hot. But the main reason for that is Venus has experienced what we refer to as a runaway greenhouse effect. It's had at some point, we think, oceans of a variety of chemical compositions. I think of methane and water, right? I'm putting you on the spot.
Yes, no, I think that's right.
Oceans of methane and water, I believe, that they've evaporated, and both of those are incredibly powerful greenhouse gases. And so once they evaporated, they've trapped the heat in. And so the reason that it's hot, actually, quinoxically, is not really because it's close to the sun, it's because of the composition of its atmosphere. Has got anything to add? I think we can start moving closer towards the Earth. Okay, so moving a little bit in towards the Earth, then we come to the second section of the course. The second section, we looked at the atmosphere. We did that in two parts. The first part was entitled Light and Air, where we look at the physics of how light and air interacting makes the planet habitable. And then we looked at the circulating atmosphere, how we don't just need to know about the chemical reactions and the physical reactions, but we need to know about how the atmosphere moves. On light and air, then Tshiamo, again.
A little summary.
Yeah,
Okay,
what's the most important thing? How does light and air make the planet habitable?
Basically, on light and air, remember we started it, and before we started, we realized that with the Earth being just a simple bare rock that is too cold, so what we did was that we added atmosphere. Yeah. So as we added atmosphere, with atmosphere, we realized that there's a phenomenon called greenhouse gas, and then with the greenhouse gas, because all the light that comes from the sun rays gets hit on the Earth, and some of it gets released, some of it gets trapped, and then the Earth itself releases infrared, and then some of those infrareds get trapped by the greenhouse, and that essentially causes the Earth to be extremely hot. Yeah, so that's what we took away from. Exactly.
Sorry, the atmosphere acts as blankets.
Sure, and but not. I mean, extremely hot. Much
warmer
than calculated
than
before.
Calculated,
but actually, you're right. If you do the calculation with a static atmosphere, so if we repeated, we started with not too hot. We calculated the temperature of the Earth. It should be far too cold. If we then add an atmosphere and we calculated the temperature of the planet, we need calculus to do that, and we don't teach that at school in South Africa, right? And we actually do in England, but I mean, you know, so we don't go through the calculation on the course, but if you did that calculation, fascinatingly, the Earth would then be far too hot. We'd have an average temperature of about 33 degrees, which again, in Limpopo, you might think sounds about normal, but actually that's not normal for the Earth. Not saying that Limpopo isn't normal, by the way. Yes. What I mean is in a scientific context, that's not average. Limpopo is a very hot place. And so actually with that calculation, the Earth should be far too hot. So that brings us to the fourth lecture, which is the circulating atmosphere. It turns out that in order to explain how we start to get to a more amicable and livable temperature, we actually need the atmosphere to move. And so in circulating atmosphere, we see that because of the way the Earth tilts and orbits around the sun, a little bit back to the astronomy, we get more light towards the tropics than we do towards the poles. It changes with season, and we'll come a little bit more to that later in the course. But just to say that somewhere between the tropics, we have the most incoming radiation and the least at the poles. And at some point, a few hundred years ago, maybe a couple, a guy called Hadley observed this and thought, well, okay, then the air is most likely to heat at the equator and rise, and cool at the poles and sink. And he proposed this idea of a Hadley cell that circulates the air, but also actually distributes heat. So it's powered by the differential heat between the equator and poles, and it acts as a way of dumping heat from the equator to the poles. That one cell doesn't in fact happen thanks to something called the Coriolis effect. The Coriolis effect is a way in which the air that's moving from equator to the poles gets diverted. It gets diverted because of the spin of the Earth. And we went into some detail. I'm not going to go over that too much, but that also has an unusual effect that it breaks up this one cell into three. And that's the main model that we presented of how the atmosphere circulates. So I'm going to dip into some questions. The first is one that we've also had online. I don't have who it's from. Did we see it online? The sky, what's the sky made up of? I've lost the student's name, we'll get it now, but the student asks what the sky is made of. It's an interesting question, firstly, because how do you define the sky? I suspect
a detailed explanation as to why
the sky is made of. Julian Wardo. Okay, so Julian, it's an interesting question because firstly, different people might define the sky as different things, and maybe at different times of the day. I'd imagine that in daytime we'd look at the sky as up there we're probably looking at the upper atmosphere, but at nighttime you probably define the sky as the stars, and they're obviously very, very different things. The stars are a lot further away than the upper atmosphere. But I'm going to assume that you mean the upper atmosphere. And so the upper atmosphere is made of atoms and molecules of gas, which are whizzing around at a high volume as per the kinetic theory of gases. Specifically what? It's probably, by that point, and I stand to be corrected, mostly hydrogen and helium that we're looking at the scatter from. Because the gases that surround the Earth are held by gravity. So around us in the troposphere, we've got much bigger particles. You've got soot, you've got dust, you've got sea salt, aerosol. But as you get up to what we would refer to as the sky, then it's only the lighter, smaller particles that can actually break free from gravity under this kinetic theory of gases model they're flying around. They can break free from gravity and actually reach up there. So when you're looking at the blue sky, and we talked about Rayleigh scattering and how the shortwave radiation is scattered by the smaller particles up there, I imagine the smaller particles we're meaning are hydrogen, helium, perhaps a bit of oxygen that's escaped beyond the ozone layer, perhaps a little bit of nitrogen, but I would imagine mostly the lighter elements. Anyone? At the beginning of space, it's just hydrogen and helium, right?
Yes.
So there's
a tiny bit of lithium and deuterium, but mostly hydrogen and helium.
Yeah, I'm ashamed as a chemist. I forgot about lithium and beryllium being light because you generally see them as a metal. Sorry. So there's a transition from mostly nitrogen at the surface to mostly helium at the top. And I would imagine what we're looking at the blue sky is mostly from helium hydrogen. Next question is, why are eyes so poorly sensitive to violet and strongly sensitive to blue? And that comes from Nontebeko Sitole and Tshiamo.
Okay. So the reason why our eyes are poorly sensitive to violet color is because of our retina. The violet color is about 400 nanometers. So, and then what we see is from just about 450. So that's why we're strongly sensitive to blue light as opposed to violet.
And it's probably evolved like that, right? Because we just get more blue light from the sun.
Yes.
The solar spectrum is, our eyes are basically evolved to cope with the solar spectrum. I guess the question arises, there was the explanation of why the sky is blue, and that short waves are preferentially scattered by these small molecules. So then why don't we see it as violet? I think it was in your talk, right? The bees would see it as violet.
The bees would see it as violet because they're more strongly sensitive to the kind of purple than us.
Sure.
Yeah.
But I wonder then why the difference between us and bees, because obviously we've both evolved under the same sun.
That's a very good question, really.
It's quite fascinating. If you look at flowers, white flowers under ultraviolet light are not white. So the bees are not seeing white flowers, they're seeing quite an exciting pattern. But I wonder why we've evolved. I guess we'd have to get somebody who's human evolution oriented.
Yeah.
Why?
I think most maybe like a person who studies like animals, because I've heard that even animals themselves don't see colors as we do. So if you understood how animals see them, and then we find in animals that see color as close to us, then maybe that could explain why as we see it as blue as opposed to violet.
I suppose you could extend it to sounds as well. Why do dogs have different frequency sound to us? And I don't know.
Like dolphins, for example.
Dolphins have the ocean, right? That's going to be a different medium. Okay, but the answer to that is then I don't know completely. But nonetheless, our eyes have evolved that way. The retina has evolved that way, that we see blue more strongly, and that's why we're seeing a blue sky and not a purple one. The next question is from Dina Mukari. It's a long one. Prepare for my reading. I'll do my best. How to explain the South African climate in terms of rainfall? Like, why does it rain in Cape Town during winter and everywhere else during summer? That does seem strange. Why does Joburg have high variability in terms of the minimum and maximum temperature compared to other cities in SA? Is it true that Johannesburg has less oxygen because it's on a high altitude? Lots of questions.
Yeah.
Bringing me back to South Africa, which is nice.
I don't know if I'll be able to answer them without using the board.
Ooh.
Yeah, because I think I'll explain more if I draw. But anyway, I'll try.
Yeah, I don't think we'll be able to see them.
No, it's fine. So the first question is, how do we explain the South African climate in terms of rain, Cape Town versus the other part of South Africa? So firstly, as on Cape Town's southwestern Cape is a Mediterranean climate, and its rainfall it's influenced by the frontal systems, your cold front, and the other part of South Africa, it's a semi-arid climate, and most of its rainfall is influenced by convective system. For example, the influence of the intertropical convection zone, your extratropical cloud bands where they extend from the Angola low in Angola, and then the cloud band extends to the southwestern Indian Ocean, and also due to the influence of the warmer Agalas current. So, and then to the next question, why does Johannesburg have a high variability in terms of minimum and maximum temperature compared to the other cities in South Africa? Sure. Okay. So yeah, this one I need to draw, but it's fine. I'll just explain it. So we know that South Africa is under the influence of high pressure or an anticyclone. So normally in winter, the high pressure it's situated in the interior of South Africa, and then Joburg it's about 1.7 of altitude from above sea level. So during winter we have an escarpment, and then we have this high pressure over the escarpment. We have the warm Indian Ocean. So the high pressure, it has subsidizing air, and then we have a warm. The plateau is cold. We have the warm air coming from the Indian Ocean, and then there's an invasion layer in between there, the warm air and the cold air. So the warm air from the Indian Ocean, because of the invasion layer, it can't move over the invasion layer. Hence, the part of Joburg it's more cold. It's cold in winter, and also the other aspect that can lead to minimum temperature in Johannesburg, it's the microclimate of the city or urban heat islands. And then in summer, the reverse happens. The high pressure is still there, but it's weaker. So we have the escarpment, and there's no invasion layer. So the warm moist air from the Indian Ocean is able to climb over the escarpment, and then the warm air can penetrate, if I might say that. Yeah, Johannesburg, I think I tried.
In terms of the high variability in Joburg, isn't the factor that it's far from the ocean important? Because the ocean has the highest specific heat, keeps the temps, and ocean climates get moderated, right?
Yeah.
Okay, and then the Joburg has less oxygen. Yes.
Yes, it does because of altitude. Yeah.
I struggle to sleep in Joburg.
Yeah.
Right? Yeah. If I get to Joburg the first night, I can't sleep because at the point where my breathing becomes unconscious, I don't get enough oxygen, and I wake up, and it's really annoying.
So surprisingly, I was in Pretoria this past week, and the first few days I struggled to breathe.
Yeah.
I've spent a year in Cape Town and got acclimatized to the humidity. I had to sit with a little humidifier just to breathe because I couldn't get oxygen in.
And you certainly notice when you try and climb a couple of flights of stairs.
But what's fascinating actually is that Neville.
I just want to interrupt by saying that my problem with being in Gauteng relative to Cape Town is not the oxygen, but the humidity, which is often very, very dry relative to the Western Cape in winter especially. And then, of course, you get these electric shocks, the static electricity, which makes me crazy. I can't touch a doorknob without the elbow.
Thanks, Neville. The other fascinating aspect of it, and the good news for people in Gauteng, is that your body actually adapts to it by producing more red blood cells, a higher concentration of hemoglobin in the blood, which means that you can actually survive with the lower oxygen. But it also means that if you come and play sport at sea level, that you have a competitive advantage because you can actually get more oxygen to your muscles faster. So yeah, you guys from the high veld, you have no excuse for not beating us in physical activities.
But the coastal people tend to be outdoors more often and more physically active.
Is that true? The weather in Pretoria is better. I mean, we have like 3 months of miserable. Maybe Durban.
There's a lot more hiking and ocean-related sports that can be done there.
You don't want to start that conversation with somebody from Gauteng. They'll always correct you that there's actually plenty to do there. And actually, to be fair, there is.
No.
Yeah.
It's going to do outside, not in terms of physical exercising and whatnot. Down here, we've got it done.
Fair enough. Okay, a lot of that also the answer came to the oceans, and we're going to come to them just now. Just the last one is on the atmosphere and physics and chemistry, is from Bonolo Mokatsi, who asks, how do we measure the concentration of greenhouse gases in the atmosphere? So that's a good question, and as the chemist, I guess I'll take that. One of the part of the response has to be is how do we measure it when and where from, right? So how do we measure it now if we want to measure it in this room? The answer is simply something called spectroscopy. And I think most people will be familiar with the idea of spectroscopy, in that we take a cell of the atmosphere, we shine some sort of radiation through it, and various different chemicals, including the greenhouse gases, will absorb specific parts of that radiation. And in fact, with greenhouse gases, the clue is in the name. We know that they absorb infrared radiation, which is released by the Earth. So all we have to do is, if we know the volume of a cell and we shine infrared radiation through it, we can calculate the concentration of the greenhouse gases by knowing how much of that infrared radiation was removed. So that's pretty simple. The question becomes more complicated if we want to know how much greenhouse gases are somewhere we're not, say over the open ocean where there's no ship, or 3 million years ago. And you'd have found in the talks this week, hopefully, that we talked about how we can actually find bubbles of gas trapped in ice cores and trapped in sediment cores. So that's how we can tell about the concentrations in the past. And then the same technique applies. We put them into a fixed volume cell, we shine a light through them, and we can calculate the concentration. The second one would be in a remote area, and then we're talking about the field of remote sensing, which I haven't thought of for a long time. Do you do?
No, I'm not involved.
You just sit in the room with them.
Yes, I sit in the room and hope that something comes in.
But even remote sensing is where you use a satellite to look at either the light coming back from the Earth or the light being shone from a laser on Earth. It works in a similar way, but obviously you've got the difficulty that the length between you and the sample is massive, and that you have to do special things to try and account for that. But principally, if I had to answer in one word, the answer is spectroscopy. That's about us on the first half.
I have a question
on
this one. So, like, beside that instrument, so how do they measure the methane from, let's say, cows?
So specifically the methane from cows?
Yeah, from cows.
That would be very difficult. I mean,
the climate change thing.
I mean, you get inventories of how much methane cows put into the atmosphere.
Or they don't measure it.
But I don't think that's back done from somehow knowing that this molecule of methane is from a cow and this one is not. That's done by knowing how many cattle there are in the world and measuring how much one cow farts. Actually, it's not farts, right? It's burps. I recently learned that cow farts is a misnomer. They burp more methane than they fart.
Oh, okay.
And that I do know that there's a patent out there for a hat that you put on cows that puts a device over them so to collect their burps and therefore stop.
Sort of like a breathalyzer.
Sort of like a breathalyzer for cows, right?
I want to say, Carl, that there may well be a method of identifying the source of a particular gas or
I would have thought so, yes. Go ahead.
They used fractionation of isotopes
to
identify the source. So there possibly is a way, although I think it'll be more to do with what the cow eats rather than what the cow burps. But either way, you might well be able to tell where it's from.
And wouldn't you have the problem that if a cow and a giraffe were eating the same food, that they'd have the same isotope signature on their methane?
No, I don't know the answer to that, but it's not impossible. I mean, what's important is that different isotopes do fractionate in different natural processes, and using that, we can identify their origin. So, for example, ivory, we can identify where ivory is from, more or less, without having any other sample other than the ivory by virtue of fractionation of isotopes.
Perfect. Thank you, Neville. Before we move on to the second half, and I'm very, very proud that we're halfway through the work and halfway through the time. That's actually a personal best for me. But before we do that, I'd like to come to any questions from online.
Okay, so one of the first questions is, could humans colonize this planet?
Haven't they already?
Yeah, I'm assuming you meant us. So Marco Sonke Madzeba asked, why is it that the Earth's moon does not have the same atmospheric composition as the Earth, considering that they both have gravity to pull a molecule?
Great question.
For me, I would think about the composition of and size of the planet compared to the moon. I'm not sure.
Can I just interject quickly and say that the first question was about humans colonizing Earth, right?
Yes.
Yeah, well, I think what that probably means is, are humans aliens?
Okay.
I think that's probably what it means.
That is actually one possible theory, is that life on Earth could have been seeded from another planet by
Life on Earth, yes.
or a meteorite with some microbes on it arriving from another planet, and then those microbes, through the process of evolution, eventually end up being us and all the life we know on Earth. So that is a theory.
That's indeed.
Oh, sorry. Sorry.
That answers the question about life on Earth. It doesn't answer the question about humans.
Yes.
And the answer is no.
Well, maybe I won't comment further, and I'll let you cover it. And the rest of your...
Surprisingly, I read something just recently when they found the lake or the water mass on Mars. Was, could humans have actually originated from Mars and then moved to Earth and colonized Earth? So I guess it's still
life or humans?
I was going to say
life.
Humans.
Human life. Okay, so I think humans, as we know them, no.
Life.
But life, by which we mean some kind of microbes, possibly.
You've got the problem of the fossil record, right?
Yeah.
That humans have been here since the start in one form or another, going all the way back. There's no moment in the fossil record where they suddenly arrive, which would falsify that.
Can I just alert people to this? Although I see I'm in mirror writing. I don't know if I'm in mirror writing on your side.
No, you're fine.
This book is called Sapiens by Yuval Harari, and I strongly recommend this to anyone from anywhere, for any reason, other than it's a brilliantly written book. You can also get it as an audio book, which I have, because it's too long to read. I'm too lazy. But this has got an incredible story about human origins. Yeah.
Okay, thank you, Neville. Yeah, that is a great book on human origins, and that will also be something we'll come to later in the course.
So just talking about atmospheres, which I think was part of the question. It's not just a question.
Oh
of
yes, back to the question.
Yeah, it's not just a question of size of the planet. Also, magnetic fields have a big role because it's actually the Earth's magnetic field that protects us from radiation from the sun that would strip all of the atmosphere away. So the magnetic field acts like a protective shield that diverts all of the radiation from the sun around us and allows us to keep our atmosphere. And so compare us to Mars, for example. Mars is a similar-ish sized Earth, but it doesn't have an atmosphere because it doesn't have a magnetic field. So the radiation from the sun has just stripped all of any atmosphere that might have been there away.
Okay, that's new to me.
So
Mars doesn't have a molten core, therefore.
Probably not. We actually think that Mars probably did have a magnetic field and an atmosphere at some point in the past. And so we know that the magnetic field on Earth, every X period of time, flips direction. And we think possibly that what happened on Mars was that at some point during one of those flips, it all sort of went wrong, and Mars ended up with no real magnetic field.
Okay.
This isn't entirely my field, so I don't know the details.
Yeah.
But that's why Mars has got that.
Would you a flip as within a few thousand years,
Yeah.
because they happen about every 10,000 years, and by all accounts, it would be pretty disastrous.
Yeah. I don't think it's going to be a fun time because life on Earth really relies on our magnetic field to protect us from the cosmic rays and radiation from the sun. So it's really, really vital to us.
Okay, that's fascinating. And I do often get students, particularly physicists, asking why we don't discuss the Earth's magnetic field and in the reasons the planet's habitable. And I have to say, I mean, perhaps we should, but we have to condense it somehow into 20 or so lectures. Otherwise, we could have you on the online course all year. But it is a really important reason, and it is one that we do miss out a little bit. Anything else?
Okay. Faith Retabile would like to know, can my habitable planet have a habitable moon? So I guess
without the atmosphere, no. Sorry.
And Lungelo Karu would like to know, is the atmosphere by the poles thinner than the rest of the world?
That is a great question, one which I feel like I used to know the answer to.
So, if I'm not mistaken, greenhouse gases plays a role in this. Also, the hole in the ozone layer.
I would have thought they purely mean physically. Thinner, i.e., does the pressure decrease more rapidly with altitude at the poles? I know the troposphere changes, but I don't know about the atmosphere. So maybe we don't know. I'm looking at the two. Either side of you are the more atmospheric scientist.
The only thing that came to mind immediately was ozone, but not exactly the atmosphere.
Can I just quickly go back to the moon atmosphere?
Yeah, absolutely.
In that our moon hasn't got an atmosphere, but we know that other moons, for example, some of the moons around Jupiter, do have atmospheres. And actually, there could be life or conditions that are conducive to life on other moons. So in some other solar system somewhere, you could have a habitable planet and a habitable moon.
I have a question. I watched this thing the other day, and it said that the moon on Jupiter is actually more habitable than Mars.
Yeah, so Jupiter has several moons, and yes, that's absolutely true. We think that some of them, particularly Europa, very much do have conditions that would make them habitable.
And what can you tell me about the conditions? Why is it more conducive than Mars?
Well, so things like, for example, the presence of oceans. We know some moons have got oceans, not necessarily water oceans, but certainly bodies of liquid, which, as far as we know, could be very conducive for life. But this is all kind of speculation at this point.
Perfect. I'm glad you brought it back to oceans, because that's where we're going now. The next section of the course, we looked at the role of the oceans. Just a couple of minutes, why did the oceans make the planet habitable? And so, Linda.
I'm going to be very brief. So the ocean make the planet habitable by redistributing heat and energy from the poles to the equator, from the equator to the poles through wind and thermohaline circulation. So yeah.
I mean, basically, it augments the atmospheric circulation, right? So we get our planet is far too hot. If we just have a static atmosphere in ocean, the atmosphere moves very quickly, but has a low. It takes a very small amount of heat as it moves. The ocean moves very slowly, but takes a very big amount of heat. And I suppose, a big part of understanding why the planet's habitable is our climate zones, and the oceans play a big role in that. And ENSO, which I'm not going to get you to explain. We have no questions on ENSO, so you get out of that this time. Although we will come to the professor at the equator. Diving into your questions, Tabello Matza asks, hi, I want to know, how does salinity vary, i.e. how salty the ocean is, with latitude, so between north and south? Which is a great question. And Asmita, you.
Okay, so I'm going to try and answer that very briefly. So salinity obviously is being affected by the amount of fresh water that's available. So a lot of the freshwater contributions into the ocean comes from the melting sea ice, precipitation, which comes from your rain, surface runoff, so from rivers into the ocean. And there's also the contributions of evaporation. So from the oceans, water is being evaporated, which means there's a high level of salt that remains there. And we know that salinity is higher in the temperate and tropical areas, where the rate of evaporation is much higher. And that is how it varies with latitude. So in certain areas, because of a higher temperature, there will be a high salinity value. And obviously in the polar regions, that will then be denser salinity values. But,
can I ask a question about that?
Yeah.
That range of salinity, how big is that range of salinity? And secondly, would there be an effect of depth on that as well at those different places?
I believe the depth would play a role because of the pycnocline that I'm not too familiar. So that's the that's the layer of or gradient layer of salinity between the upper surface and the lower surface. And sorry, what was the other part of your question?
So what is the range? Like, is it like by like 1 or 2 parts per thousand? You know, like how wide? I mean, do we get like really fresh brack water in some parts and really salty water in others, or is it just marginal? Would I be able to taste the difference, for example?
I mean, obviously at river mouths you get very very fresh water. So locally, certainly there must be a huge range, but I don't know about if we're talking about just open ocean.
Yeah.
Then I'm not sure. Oceanographers? Actually, I spent a large part of my career looking at CTDs, which have salinity with depth, but I don't remember, I have to say.
It does vary from region to region, depending on the continent. So like, for example, in the Pacific, there's the oceanic ridges and all those contributions, which would then affect the total salinity from like closer to the continent and further into the open ocean. And then obviously with depths, and you also have your contributions of different water from your seabed, from hydrothermal vents. I'm not sure if they contribute much to the salinity, but I know they have contributions of other nutrients into the ocean. Yeah.
I wonder I actually wonder why the question came up. It's quite an interesting one, which I haven't thought about for a long time. It has to be said. But thank you for that, Tabella. I hope we got somewhere. I want to press on. We learnt on the course about how when you look at sea surface temperatures, they don't actually correspond to the amount of sunlight reaching the ocean surface. And so Masego and Tini asks, why is that? Why is the pattern of surface temperatures not the same as incoming solar radiation? And giving away the answer a little bit, but linking onto that, Ndivo Mufamandi asks, what's the importance of upwelling in an ocean? Neville, I'm going to go over to you for those.
Okay, so by and large, without any circulation, I imagine that there would be a very strong correlation between sea surface temperatures and solar radiation. But because there are ocean-atmosphere interactions, and because ocean currents are moving water around, so that heat is distributed around. And this, of course, changes seasonally, because solar radiation changes seasonally as well. So there are a variety of drivers that redistribute things and keep mixing them all the time. And you get local mixing. So if the wind's blowing strongly today in Cape Town, as it is, southeast, so we're getting some mixing of the water surfaces, and that will change the sea surface temperature quite significantly. And then, as Carl pointed out, upwelling is really critical. Upwelling, as I just spoke about, in fact, I would argue that I could attribute my whole career to the existence of the wind. And that's because the wind drives water offshore, the surface water. It's like blowing on the surface of your cup of tea. You can push the water away from one point to another, and that water is replaced by water from the bottom, which is generally colder. So if water is warmed up by solar radiation, then when the wind blows, that water is replaced, and that process is called upwelling. So that does cause changes to the temperature of the water at the surface, which is offsetting the impact of solar radiation. Conversely, without wind, sometimes water can be quite stagnant, and you get what's called the thermocline, which basically is a density layer. The water at the surface, which gets sunlight, is slightly warmer and therefore less dense and floats on top of colder water. And that is really what we're referring to when we talk about the sea surface temperature. Although I want to just quickly add that sea surface temperature is measured generally from a satellite. And it's not measuring the temperature, it's measuring the radiation or the reflection of radiation off the surface. So sometimes it's a bit of an illusion that we just look at the thin top layer of the surface of the oceans, whereas much deeper down, or just even a short distance down, the water temperatures change quite significantly. So short answer, or short version of the long answer in summary, is that there generally is a correlation, but that correlation is offset by a whole lot of mixing that happens horizontally and also happens with depth in the oceans due to wind, ocean currents, and various other local processes. That's my answer.
Thank you, Neville. So yeah, I mean, principally the wind circulation, the thermohaline circulation, bring up cold water and send down warm water, breaking that pattern up, right? Reasonable? Okay, he's giving me a nod. Perfect. Next question comes from Zaben Tungwa Shlongwane. And it's a great question because it's just one of those things that would have really interested me as a kid. And that's, what's the largest ocean and deepest ocean in the world?
Okay, so the Pacific Ocean is both the largest ocean as well as the deepest ocean on our planet. It covers a total surface area of approximately 59 million square miles, and apparently contains more than half of the free water, so floating water on the planet. And the Pacific Ocean, that entire region between America and Africa, it's believed that all the continents can actually fit in that region of the ocean. So yeah, that is your largest and deepest ocean. So there are different ridges and stuff that are in the Pacific Ocean, which is why it's significantly much deeper than most of the other ocean basins.
And it's a famous quote, but it got almost trite. It's so famous that we know more about the surface of the moon than the bottom of the oceans. But it is definitely true. We know very little about it, mostly because there's little money in going down to the bottom of the ocean, whereas going into space is just more exciting.
Can I quickly say something there?
Yeah, go ahead.
Sorry, two things. One is that, well, there's more minerals. Well, I don't know if that's true, but more minerals accessible in space probably than in the oceans. But I just wanted to tell people that what you should Google is what the Earth would look like without oceans. So you can see the relief of the ocean floors. And if you measure the distance between the deepest parts and some of the peaks at the bottom of the ocean, the highest mountains in the world are not on land, but at the bottom of the ocean.
Nice one. Thanks, Neville. I had a linking bit there, but I can't remember now. So moving swiftly on, because I can't think what I was supposed to say. I do know what I was supposed to say. I see that on the WhatsApp group, there's some interesting discussions about human evolution. That is going to come up later, so I'm sort of slightly ignoring those for now as it's coming up in the course. But also on the WhatsApp group, there was somebody sharing a picture of the Atlantic and Pacific Ocean not mixing, and there was some discussion of that. So I assume that Balungile Umpolpa's question as to why the waters of the Atlantic and Pacific don't mix comes from that. Asmita?
So one of the primary factors why these two bodies of water, the Atlantic and the Pacific, do not mix is because of the difference in chemical and mineral composition.
Okay.
Yeah. So I think that's as brief as I can do.
So basically, but I mean, they would mix eventually, right? So it must be just a temporal thing.
So if you look at, for example, Cape Point, they do believe the waters are mixing, but you can actually see there's a distinct difference at some point.
I've sailed over it, but you can physically see. Yeah.
Really?
Yeah,
At Cape Point?
Well,
it moves around.
Yeah.
It's not exactly.
Not at the point, but you observe somewhere there. Right?
Okay.
Because of the
No, sorry. I just wanted to add to that to say that you get what's called a front, just like you get a cold front in the atmosphere, right? So if you look at the atmosphere, you can see a cloud bank. You can see there's a difference between the air over there and the air over here. Similarly, in the oceans, you can see fronts, and sometimes they're separate, as you correctly described. Their properties are different, and they can mix with the right forcing, but where there are strong differences, especially in density, which is from temperature or from whatever other characteristics, salinities we spoke about earlier, they certainly will stay separate until they're mixed. by force.
Okay, thank you, Neville. One last thing in the ocean. Oh, two last things in the oceans. We had the question from Percy Moleele about why is it that the oceans are blue? Are they just reflecting the sky? So we could envisage an interesting thought experiment where the sky was a different color. Would the oceans be a different color? And as a chemist, I'll take that one. And very simply, water absorbs red light. So the ocean water appears blue, but only if there's a large amount of it, because the light must be reflected internally in the water. So water will appear blue when light from the sun shines, penetrates the surface of the water, and then as it goes through, the red light starts to be removed, then it gets reflected and comes back, the red light is removed, and so once the red light's removed and it comes back to your eye, it starts to appear blue.
Sort of like a prism.
A prism effect, but it means that water doesn't reflect blue light, right? It absorbs red light. It's a subtle difference that means that water only appears blue when you have quite a large volume of it for that red light to have been removed.
Because if you look at shallow waters, you
You can't really see it.
blue.
Or a glass. Okay, that's a really bad example because that bottle is blue.
And also, you have to have, it has to have had white light with all the range of light as a source in order to absorb part of it and reflect other parts. And secondly, to say that sometimes the ocean can be red, right? And it can be red when there's a red tide. So you may have seen this before when there's a bloom of algae, which are red in color, as in they emit red light. The ocean appears red or green, as the case may be. But in general, Paul's point about water holds.
Yes, that's absolutely right. The colour of the ocean is then augmented by the organisms in it and also by sediment, and chemical composition. But should the ocean have been just water, it would be blue. Algae tend to add a green tint, although in your case of a red tide, a red colour. But yeah, the predominant colour of the ocean is in fact blue. So just a couple of last bits, one last one in the ocean section, and that's going to our professor at the equator quite nicely sums up. So just to remind you, we did a little bit of a case study, an African case study on the Coriolis force, where we have anywhere pretty much you go to the equator across the African continent, you will find people there who are willing to show the tourists a demonstration of the Coriolis force, where they take a bucket of water into the southern hemisphere, and we see the circulation go down one way, and then they go to the northern hemisphere and it's the other, and then on the equator it goes straight down, which is an absolutely wonderful and exciting demonstration, aside from the fact that it's complete and utter nonsense. And completely wrong. So we did that as a little bit of a case study on the difference between science and ethics questions. And we were looking at the idea that, oh, by the way, it's called the professor because the one guy in Kenya calls himself the professor before he explains the Coriolis force. And we used it as a way of trying to start thinking about the difference between science and ethics questions. Scientific questions that have a correct and knowable answer, and ethics questions about what we should do, which have no correct answer. And I hope that, and this comes towards the test, one of the big learnings from the case study is just because we know the answer to the science question, is he showing the Coriolis force? No, it's a hoax, right? The Coriolis force isn't being shown in his demonstration. But the fact that we know the answer to the science question doesn't mean that we therefore know the answer to the ethics question. What should we do about it? And lots of physicists are very cross with this guy. They want his demonstration to be shut down, but it presents really interesting and difficult ethical questions as to what we should do with him. The one question we had on this was from Poncho Mashelangako, of course. And he asked, is it due to the scale of the demonstration that the African professor did that the physics referred to the demonstration itself as a hoax? And I mean, the very simple answer to your question is yes. The Coriolis force simply doesn't operate on that time and space scale. And there's Professor George, who started Access, once took me through the calculation, and I'm going to try and summarize it very simply, and that's that the Coriolis force will have an effect on a very, very large body of water in a short time, or it will have an effect on a small body of water on a long time. So for your toilet or your sink to experience a significant Coriolis effect, it would have to be draining for several thousand years. And it doesn't. It drains in 2 minutes. Within the 2 minutes that it drains, the Coriolis effect simply isn't significant. So I imagine, and you guys can do this, go and watch your toilet or your sink flush 100 times. Out of that 100, okay, yes, somewhere that's not experiencing a drought, you could do this experiment. Out of 100 times, maybe 51 will go anti-clockwise because we're in the southern hemisphere, but it's a really subtle effect. I would think you would have to do it 10,000 times before you found some sort of bias, because it's really insignificant on this time and space scale. So the guy is definitely a hoax. That's very clear. By the way, some physicists in the States in the 60s aimed to prove this, and they got a swimming pool that slowly let out down a funnel. And on a swimming pool scale, it takes a few months. And after a few months, sure enough, the Coriolis force was effective, and it started to circulate the way you would expect it to. Okay, anything from online before we move on to modeling?
Okay, so let's try and go with this. So Nondomusa wants to know what makes the observed patterns of the ocean surface temperatures to be inconsistent with the amount of incoming solar radiation.
Okay, so hopefully Neville covered that when we did the cold welling water. So maybe that was before that one, I hope.
Okay. Ravura would like to know, how do atmospheric radiation, I'm assuming windows, relate with greenhouse gases and climate change?
That's a very complicated question. Would anybody like to take it? Or shall I?
Can you repeat the question?
How do atmospheric radiation windows relate with greenhouse gases and climate change?
Windows. Did she say window?
Radiation windows. So the gaps in between where radiation is naturally absorbed. Shall I go ahead?
You better, because I don't understand the question or know the answer.
So principally, if you look at the radiation that we receive from the sun, then the solar spectrum is a nice curve and it peaks around the visible. If you look from space at what's reflected, then that curve is eaten into by little bands. And that's where natural gases are already absorbing the sun's radiation. So it's greenhouse gases, water, carbon dioxide, already absorbing those bands. And actually the water one is often maximized. So what that means is if all of the radiation that falls, and this is bands by wavelength, sorry, I should say. So specific wavelengths don't make it back into space because they're absorbed by greenhouse gases. So if the water one is completely maximized, i.e. 100% of the radiation emitted by the Earth doesn't make it back into space because of the absorption there, then adding more water to the atmosphere won't increase the greenhouse effect. It won't make the planet warmer because that one's already been 100% taken out. But in the gaps where 100% of the Earth's radiation is making it to space, that's where you'll have a really big effect. So a lot of the CFCs that we produce are so important in terms of climate change because they absorb in those gaps. There's no natural thing absorbing there. And so they have a much bigger effect because there's no chance of those gaps being already taken up by natural stuff. I think that's what the question is asking, and I hope that's an answer.
Those gaps are also relevant to astronomy because we can only observe radiation from stars and galaxies in the gaps where the radiation can come through the atmosphere.
Sure.
So we can have optical telescopes on Earth and we can have radio telescopes on Earth because they're two gaps. But things like infrared, UV, X-rays, we can't have those kind of telescopes on Earth. We have to put them in space. So that's why we have to send satellites out to, for example, make X-ray observations of stars.
I actually realized that.
Neville?
I just wanted to ask, there was a question about nutrients, which I see is no longer on the list. Is that, have we passed it over, or?
We have passed it over, but if you'd like to answer it, you can.
Okay. Well, I thought about it, so I just said this.
Okay, fine. Would you like to do both the question and the answer for me?
Yes, if I recall, the question was about the fact that there are nutrients in the ocean, especially deep in the ocean, and why is it that humans can't use them? I think that's essentially what the question was asking.
Sure, and it's from Palmer Yossi.
Yeah, and the answer is that we do use them in a number of ways, one of which is that we mine them. Phosphate, for example, which is limiting, is available at the bottom of the ocean on the ocean floor, and it's being mined. So we do use a lot of minerals directly from the ocean, which we harvest. But essentially, those nutrients in the form of their dissolved state is not that easily available, because the energy costs in concentrating them enough and harvesting them will be just too great. The only way we can really use them is if natural systems concentrate them in biological processes, and then they go up the food chain where we get them that way. That's the short answer to that question.
Nice one. Thank you, Neville. Any more from online?
Okay, so Archmuna would like to know, are there any traces of humankind on planet Mars? I guess not that we're aware of yet.
There are a few rovers up there that we've put there. So rovers like Curiosity and Spirit and Opportunity that we've sent up there, and they, in fact, two of them are still sending back images and data. So I suppose they are traces of humankind in that we put them there as humans. But certainly no evidence for human life.
and famously, Curiosity has finished its mission, right? But actually wakes up once a year to sing happy birthday to itself. So if you ever think that you're lonely and depressed, think about that.
Okay, Rahura asks, do we know the average surface temperature of the moon and of the Earth?
Yes. The Earth is around 15 and going up a little bit. I don't know about the moon. I'm sure we do know.
So it's much hotter on the side that's facing the sun than the side that's not facing the sun. And this links to what we've been talking about in some way about atmospheres and oceans, because the moon doesn't have any oceans and doesn't have any atmospheres. So it's very hard to transfer heat from one side to the other. And I think we looked it up, and it was about 300 degrees on one side and minus 300 on the side away from the sun. So.
Can I just make a point here, which is just to make a point about what average means. And it's important to know that often there's no such thing as average. In other words, average is just a useful number to describe something, but never really represented in a real state. So if you take the average of the moon, for example, the average is meaningless because they are so different on either side of the moon. Similarly on Earth, the average temperature on Earth is only useful for some applications, but really what's important is how the extremes of temperature vary and are changing over time. So that's just a point I wanted to throw in.
Thank you, Neville. Check out.
Yeah.
Okay, so we're going to move on to modeling. Modeling.
There was one more.
Okay, sorry.
So Lungiello asks, what is bigger, the sun or stars? And what would happen if stars were closer than they currently are?
The sun is a star.
Well, yes, exactly. So the sun is a star. The sun is a very typical star, actually. So there are lots of the stars that you see in the night sky are very similar to the sun. And what was the rest of the question?
So what would happen if stars were closer than they currently are? We'd probably be having more than one sun.
Yes, and in fact, we know that lots of stars that we see are actually pairs of stars. They're what we call a binary system. So a lot of the stars that we see are actually two stars orbiting each other. So lots of planets actually do have two suns. Planets in other solar systems than our own do actually have two suns. So. That
brings me on. I'm digressing, but it's a great one as to why is night dark, right? Because with billions of, is it the dark matter issue?
Well, no, this is actually kind of comes back to the concept of the observable universe and is in some ways proof for the Big Bang, right? Because the opposite to the Big Bang is the steady state universe, where the universe has just always been. And if you say, okay, the universe has always been and it's infinite, then there's been an infinite amount of time for light from all of the stars in the universe to get to us. So everywhere you look in space, everywhere you look in the night sky, there will be somewhere along that line of sight a star. And if there's been an infinite amount of time, that light would have reached us. So everywhere you looked in the night sky would essentially be a star, so it wouldn't be dark at all, it would be bright. But because the universe is only 14 billion years old, the furthest away we can possibly see is 14 billion years. So we can only get light from the first stars that formed 14, well, it was less than 14 billion years ago because stars don't form straight away. So the fact that the night sky is dark is in some ways proof, is evidence for the Big Bang theory.
Okay, fascinating, thank you. I'm going to press on then to our section on modelling, which is our last little bit for today. Modelling is something of a sidestep from the main story of adding different reasons why the planet's habitable, but it becomes very important, particularly in Earth systems science, because we do rely on modelling more heavily possible than a lot of other sciences. Although one of the things that we saw in the modelling talk is that models are all around us. Models are simply any representation of a system in some form other than itself. But what we tend to think of in models is not so much, well, you might think of fashion models, which are a type of model, right? That's modeling an item of clothing for how it would look on you in some other form than yourself on someone else. But really within Earth system science, a lot of it tends to be numerical models. Occasionally when we come on to the wishy-washy biology side, then statistical models, and we looked at those different types. But the big reason for wanting to do numerical modeling within Earth system science is that we don't have a second Earth. So it's not like we can just do a physical model of these very easily. We couldn't make another Earth. And we can't run experiments on the planet because we're all here. And so, you know, finding out if changing this actually causes it to become uninhabitable would be a bad experiment to do. So models become very important. We saw this, you know, this slightly strange quote from George Box that all models are wrong, but some are useful. People have had a lot of comments on that. I mean, to break it down, I mean, obviously, the statement all models are wrong doesn't mean all models give all wrong results. And I think, am I jumping ahead?
Yeah, it's fine.
Is it fine? Okay. It doesn't mean that all models give all wrong results all the time. It just means that because no model is actually the system itself, then no model can ever be expected to give all of the same responses as the system itself. So for example, we saw a model of the hydrological cycle in the talk, which featured rain. But should I stick my hand onto the bit where we were seeing the rain, my hand wouldn't get wet. It's not exactly the same as the thing itself. It doesn't give me the impression of being wet like rain does, but it does help explain some aspects of it. So that's really a little bit about modeling. We looked at parameterization, the fact that actually when you design a numerical model, you can't solve every single equation. It's not possible. So scientists borrowed a little bit from artists. Artists realized that when you paint a field of grass, you can't paint every blade of grass. They would have been there their entire career. So they found a way of actually giving the eye the impression of a field of grass without painting every single one. Parameterization is a very important process in modeling. That's where you try and give your equation the impression of a large amount of things. Like, for example, if I'm modeling the albedo of Earth, I don't want to model every point where a wave happens in the ocean. I just want to know what's the average effect of all the waves in the ocean. So that's where modeling comes in. Just a couple of questions on that before we start to wrap up. The first one, which is a huge one, and so I'm going to ask Belinda as our expert, but I'm unenvious. Julian Nwado asks, how are models able to predict the weather? How can we possibly know what's happening in the future?
Okay, so I'm just going to give a brief.
Please do.
Yeah, of how the whole thing is done. So, like, yeah, firstly, to predict weather, you have myself observation or station data and also satellite data, and then from there you must feed that data, which is called initial condition, or the process is called data assimilation, into a three-dimensional atmospheric model. After feeding that initial conditions into the model, you must use your basic or your mathematical and physical equation of the atmosphere to sort of predict. How can I say? Yeah, if you feed the data into the model, it's 3D, and then from there you step forward the model, and then the output of all those steps in each point in the model, yeah, help you to predict or forecast the weather. I don't know if that makes sense. Yeah.
Basically, you predict what would happen.
What will happen, but you must use your your data. You must have
So you need
data
to have
first.
like pre-existing
Data,
data,
yeah,
before
then
you
fit
can
into the model,
predict
yeah.
it. Okay.
Yeah. So you need something. It's kind of like extrapolating.
Exactly, yeah.
What's going to happen without data points? You can't
really predict. Yeah.
And I guess because you're extrapolating, that's why the further in the future you go, the less accurate the models are.
I was going to actually say, like, half the time you look at the weather and it's not really how it is. So is it really like, is the predictions, is it necessary to say that you're predicting weather when most of the time it's incorrect? Like, so what's the point?
I'd say it's Mother Nature's decision of making us appear correct or not.
Weather forecasting on a 2-day scale is very good, right? It's very rarely wrong nowadays. Yes.
Not in Cape Town.
Cape Town, you go to the other side of the woods.
Well, okay, I mean, Cape Town has microclimates, but if you look at the amount of rain Cape Town will receive tomorrow, then over the whole of Cape Town, it's very, very good.
But if you want to know how much rain Cape Town's going to receive on a day in 4 weeks' time,
very bad. And that comes down,
yeah.
sorry, I just popped out. I don't know if you covered that. It comes down to chaos theory, right? That's actually all you're doing when you're predicting the weather is simple Newtonian physics. You've got a bunch of particles in the atmosphere and they move under Newton's laws. And that's Newton's laws, whether they're called laws, right? We talked about theories and laws earlier. They're very, very rigorous. The problem is you don't know where all the particles started. And there's the analogy of the skier who drops a wallet on a ski slope, that it will take a path down and there's lots of little undulations on a ski slope. So it'll take a path down and it will bounce around to the bottom. But if you change the position at the top by just a small amount, the trajectory can completely change to the bottom by several kilometers and he can't find his wallet. And so the problem is we don't have a weather station every square meter of the atmosphere, so we don't know where all the particles are to start with. And that means, you know, with the wallet analogy, if the wallet is quite close to the top, then you're going to get its trajectory pretty correct, even if you've missed its start position. But as further you get down, then the position becomes more and more uncertain. And so weather forecasts beyond 2 days, famously, and I think this also comes from Professor George, he said if you would take a weather forecast for 5 days, you're actually better to look at what the weather was like on that day last year and use that as a prediction. But nonetheless, I suppose one thing is that weather apps insist on giving you 5-day predictions, which are useless.
10 days.
10 days, and people look at them and think and believe them, and then when they don't happen, people get upset, right, and think that weather prediction is useless when actually it's not. You just have to know the limitations. Okay, I'm going to press on. Ketchapane Modise asks, is it possible for us to measure the ocean productivity using modelling? And I'll leave it there for you, Neville. Do you want to just add a bit on that?
Well, the answer is no. You can't predict anything with a model. You can, I mean, you can't measure anything with a model. You can predict something with a model, and then you have to verify it. So one of the key elements of modeling is to verify. So just to basically go back on what's been said, if your model has a good representation of the past, then you have some confidence of its usefulness in predicting the near future. And depending on the scale and the resolution of how much detail you want to do, so you lose power accordingly. So for example, if I want to look at something at the range of square meters or square kilometers, that's quite high resolution. And so my predictability is good, but only close to the point at which I'm starting to look at the future. If I'm looking at something that's so for example, I know it's going to get cold in winter in the Western Cape. I don't need a model to tell me that, but in a sense, I am predicting the future, right? So,
Neville,
yes.
You are using a model there. You have a model of how the Earth progresses around the sun, and one side faces and the other. You are modeling it.
Absolutely. But what I'm pointing at there is that I have something based on my knowledge of the past, which is that winters are cold, and it rains more in winter than in summer. That's an historical record, and on the basis of that record, statistically, I can say with some confidence that it's going to get cold and wet in winter. Similarly, with productivity or any other property that I want to look at, models can't measure them. They can only predict them, and it's critical to verify your model to see whether your predictions were correct or not. So just to summarize, or just to end off, when we look at people using climate models to predict things, what they often do in their talks is they will say, well, I got all this data, which is actual measurements, and here's my model, and I went back to the past and ran my model forward as if it was predicting, and I saw that it was very good at predicting what did happen. So therefore, I have confidence in what it will do in predicting what will happen. And so then you can use the model to estimate or guess or predict, and then you have to verify afterwards.
Okay, thank you, Neville. One last question on here, which I'm just going to include quickly because it's a fun one, comes from Chuster Nendlanglavu, who asks, is there any chance that the Earth's rotation or spin would reverse? And if yes, how would that impact us? I think we all agree that the answer is no, right? And if it did, the first impact would be that we would all fly off the Earth immediately because it's spinning very fast in one direction, 1,000 or so kilometers an hour. If it then suddenly was going 1,000 kilometers in the other direction, we would all fly off into space. But let's imagine for a minute the Earth had always been going the other way, and that the panel here was sat on the coast of South Africa, watching sunrise off the west coast with a cup of coffee. How would our lives be different? Interestingly, there's been a recent model study to look at that, and one of the ways that our lives would be different was obviously Cape Town would be tropical like Durban, and Durban would be dry like Cape Town. And interestingly, the Sahara Desert would be a jungle, and North America would be a desert. So I'll put those results. All of actually everything from the top of Brazil all the way to sort of Washington, D.C. would become the new giant Sahara Desert, and Africa would end up being all a jungle or actually grasslands, which is quite interesting. But I'll put the results of that survey up. That model, sorry.
The time frame is going to change after 3 months, a year, or?
Well, again, the model assumes that the Earth had always been that way. So it was spun up completely. It's not that the Earth suddenly stops and then changes, that actually it had always been that way. I'd be fascinated, and I don't think we've got time for it now, to look at things like biology. So, for example, proteins all rotate in one direction. Is that linked to the Earth's rotation? Would it go the other way? Or is that completely independent? I don't know. But anyway, it's a debate.
We're running out of time. I'm sorry. I just want to quickly ask, I don't really understand why it is that the Earth spins in the particular direction it does. Some planets do spin in other directions, right? I guess it's something to do with how it was formed. Is it some random decision or some random process that it's to spin one way or another?
I'm remembering from looking into this, and I'm going to hand over to the astronomer, that basically all the planets spin in the same direction except one, and that's a bit of a puzzle, right?
So it's all to do with conservation of angular momentum. So angular momentum is basically how something is spinning, and that has to be conserved. And so the illustration of this that's often given is if I'm spinning round on ice skates with my arms out and I'm spinning slowly, if I then bring my arms in, I'll start spinning faster because the total angular momentum has got to be conserved. And so when we went back to talking about the formation of stars, we were talking about how we had this cloud of gas and dust to start with, and that would have been spinning slightly, or sort of moving around slightly. And as that collapses, that has to be conserved. And so as it collapses, it has to spin faster to conserve that angular momentum. And the angular momentum of the whole system has to be conserved. And so you end up with the sun spinning and all the planets orbiting in a certain direction, and the planets all spinning generally in the same direction. And that's all because angular momentum has to be conserved. There are lots of other processes that occur, such as collisions and sort of asteroids collisions and this sort of thing that can disrupt that.
So I remember one of the 8 planets is the wrong way, and they think it's been flipped upside down at some point, right? But I can't remember which.
Yeah, and there's all sorts of gravitational interactions between planets when they were forming that can cause them to be flung in weird directions. And
I have to ask this quickly, one sentence, if I may, and that is, what if the Earth was slower, spinning slower than it does? Would that affect our gravity? Or is that just mass dependent, or faster, as the case may be?
So the spinning doesn't actually have anything to do with gravity. So if the Earth was spinning much, much faster, much, much slower, the gravitational force would be exactly the same. In terms of if the Earth was spinning more slowly, I imagine that would have a large impact on the climate. And
Coriolis force.
Exactly, all of those kinds of things. That's not something I know a huge amount about, exactly what kind of effects it would have. I don't know if they would be.
I mean, we don't notice the Earth spinning. would we notice it spinning slower? I guess not, except for the Coriolis force is really the only way it impacts us, right? I can't think of any other way that the Earth spin impacts us. Well, days would be
I was
longer.
about to say, it affects the length of the day.
Yes, so we'd have very long days and very long nights.
Yeah.
So you'd get more sleep, but also have to stay awake longer.
So.
All right, I'm going to have to start wrapping it up there. We just have a few general questions that I wanted to tag on the end quickly before we close for the day. The first one is from Grace Monyela, who asks, how does it feel to be a professional scientist? I'll put that to any professional scientist here. Who counts themselves as a professional scientist?
Oh, we all are. And how does it feel? Well, I mean, I certainly really enjoy it as a career. I really enjoy that I'm always finding out more about our universe. I find that sort of very fulfilling. On a day-to-day level, it can be quite frustrating because often things won't work. Your data won't look like how you thought it did. Your computer code won't do what you wanted it to. But certainly, I really enjoy it as a career. I don't know.
Anybody in the room before I give Neville a second?
I mean, what professionals? Personal scientists, yes, but not professional
You get
scientists.
paid.
As professional student.
Being a scientist, no.
Yes, you do.
I'm paid.
I'm definitely paid to be a scientist.
Yeah. Neville?
Well, all I want to add is that indeed it's a great privilege, actually. It's a fantastic lifestyle. I've had an incredible career, not in terms of success as much as the experience of traveling the world, meeting interesting people, answering interesting questions. All those kinds of things are fantastic. Strongly recommended. But I want to just add that that's just the science part. Because being a professional anything involves a lot of other stuff like management. So, you know, there are forms to fill in, timesheets, HR, bills to pay, life in general. So, you know, there are the advantages of what we do as scientists, but there are disadvantages as being a professional in any career in dealing with systems and processes and employees and employers. So I'd say it's a great career choice.
Okay, and I'm going to link on to that and stay with you, Neville. If the students out there actually want to be professional scientists and want to get research grants from Access for Masters and PhD, how would they do that?
Okay, so I want to explain quickly that the Access program does not issue research grants or, as it were, bursaries to students directly. That's the role of the NRF. The National Research Foundation is the national institution. I mean, there are obviously private ones as well. It's the national government institution that issues bursaries to postgraduate researchers. What we do in Access is we have program money. That means we give money to professional scientists who apply to us through a call process. So we issue a call, namely we want research done on this, that, or the other. They apply. If there's a process of adjudicating their application. If their application is successful, they get allocated research money. In that package of money is bursaries, and then they advertise the bursaries. So if you wanted to work in an Access project, you'd have to be connected to an institution who has made application for bursary money to pay their students, and there are many of them. At the moment, we have 6 programs, and we are actually about to advertise a whole lot of positions for postgraduate researchers in these projects. So it's not directly through Access, it's through the institutions that are our partners. I hope that answers the question.
No, I think that's great. Does that seem reasonable?
Carl, I need to ask you whether I can excuse myself.
Yes, you may.
I'm going to catch, not to crash, hopefully.
Please don't crash the plane.
So thank you very much, everybody. I'm sorry I have to leave you right now, but I have to go.
Thank you very much, Neville. In fact, don't actually even attempt to drive the plane, pilot the plane. Just
I won't. I assume that the pilot doesn't want to crash it either.
Okay, thank you very much, Neville.
Bye.
Before we go, very briefly, just 2 more, and then we will leave you all. First is very quick. Zandile Nglazi asks, why is the venue for HPW changing to Polokwane in December? The answer is very simple, that there happens to be one of the country's biggest gatherings of climate change scientists happening in Polokwane at the same time that we wanted to do the workshop with you guys, the Habitable Planet. So we decided to move our workshop to be in the same place. And that means that you are all, if you get accepted to the Habitable Planet workshop in December, you will all get a free ticket to attend the whole of this climate change meeting. It's called the Global Change Grand Challenge meeting, and go listen to and question and meet and have a braai with all of South Africa's top climate scientists. So although I know lots of people were excited about the idea of a trip to Cape Town, that was too much of an exciting opportunity to turn down for you guys. So hopefully we're all going to go and meet the scientists at the Global Change Grand Challenge meeting. I'll finish with one which comes up every year and will give us at least 2 minutes of interesting discussion to close out. Notife Sherzi asks, do you believe in God? Do you believe God and science belief can coexist? Asmita, you wanted to just kick us off.
So I consider myself to be somebody who believes in God as well as in science. And so in my belief, God created all of this. Science is just our medium to try and understand God's creation. Because from reading the Bible where it says God created the earth and this is what he created, from science we are finding ways where we figure out, oh, okay, this is how the earth was formed or how the earth started. So for me, it's just the link between what was created by the creator and how we are finding out what or how it was created. But that's just my take on it.
I play devil's advocate a bit. Firstly, I don't like the use of the word believe in science. I mean, we talked about the Big Bang earlier. The evidence is overwhelming. There's no need for believing in it.
You believe it's true, Carl.
You don't believe it's true. That's the point.
Yeah.
You don't have to believe.
I think that's the difference between like God and religion and science, because science does not need your belief. It needs facts and it needs whether you understand it. Whereas religion is a belief system. There's no evidence that sustains anything. So I think you can believe in God and understand science.
Yeah, I suppose taking a step back, with the belief in science, the evidence for something is overwhelming, therefore you accept it. For me, that just means that you're not a moron. If you just accept everything with the overwhelming evidence. But then religious people will say, well, then you believe in evidence. And I suppose, so a belief in empiricism, in the ability to measure things in the world. But again, I mean, the phone works, right? It doesn't matter whether you believe in science or not, it works. And so it's not that you need a belief in it, it just demonstratively actually causes progress, which seems to be a big difference. But then to put it to you, in your version then, I mean, God used to be this thing which explained why the weather happened, and explained why cows got fat or thin or why grass grew. And slowly, those have all been whittled down. And so your version is just God sort of started it off and then sits back and just watches. And then for me, that becomes indifferent, completely the same thing really as no God at all. Because, I mean, it becomes a moot point.
It does become a bit controversial. No, and again, I don't want to debate it too much. I mean, that's just from the belief. It was all created, it's being sustained, but sort of self-sustained in a way, because you believe in Mother Nature. I mean, like in some terms, science does happen to fail. For example, our climate system models, the predictions, we predicted that this will once again be a drought-stricken year for Cape Town. But we did receive rainfall, but it's still below average from what was predicted.
But then is that because of chaos theory, like I said, that the predictions break down as you go on, or is it because some supreme being intervened and made it rain more or less?
Well, this is a bit of a controversial one because there were a lot of people that prayed a lot for rain, and the rains came, but at the same time, the science predicted otherwise, and the opposite happened. So I don't know.
That's true.
I kind of want to sit on the fence on that. Like, not this, no that. Like, it happened. Coincidence, not. The main fact is we got what we needed.
Professor,
in this case.
Professor George, do you know about the Rain Queen in the Popo? Professor George famously said, and I guess it's a nice way to wrap up, of the Rain Queen in Limpopo, that if you go and stand on a hill in Limpopo in November, it's going to rain soon, whatever.
Perfect.
Okay, thanks guys. Thank you to the panel. You've been absolutely wonderful. It's been a fantastic discussion, and I hope that we've gone some way to answering all of your questions out there. Thank you to everybody watching, whether you've been sat at your own computer for all this time or whether you've joined one of the groups. It's been great to have you. Please, everyone on the course, bear in mind you've got this week's test to fill out. We're only going to take the top 20 or 30 or so to Limpopo, so it's important to get those in on time. And please, please, put your exam number correct on the test, else your exam mark goes to someone else, and then it takes me forever to figure it out, which I don't like. So if you can please find your right exam number and put it on, that will help me out a lot. Okay, guys, thanks very much. That was really super, and we'll see you for event 2 at some point later in the month. Bye.
Bye.